Hey, this is Brock Lemires, and in this video, I'm going to talk about the floating point data types in C and also how you use printf with floating points. Okay, so at this point, we've looked at what a data type is, which is basically how the program interprets and encodes information in binary. And so we looked at the integer data type, which can use ones and zeros to store whole numbers. However, in the real world, we need the ability to represent numbers with fractional components, or what we call real numbers. So an example is like pi, like 3.14. And the 0.14 is not part of a whole number. Okay, so that's a fractional component. And so we need a way to encode ones and zeros in order to represent these types of numbers. And the way you do it in modern computers is called floating point. Now, floating point is an encoding technique, and it's basically follows a standardization. It's a standardized by IEEE. It's actually 754, the 754 standard, and it talks about how you specifically use the ones and zeros in order to represent a floating point number. But let's take a look at what floating point really is at a high level. So first of all, you take real numbers and think about scientific notation to begin with. So if I have a number like this, 5326.6, I can represent that in scientific notation doing 5.3266 times 10 to the 3. So you multiply it by times 10 to the 3 in order to represent how many times or where you move the point in order to get back to the original number. And the way that scientific notation works is that you try to only have one whole number to the left of the point. All right. And so if you looked at a small number, like 0.00001602, like the charge of an electron, the magnitude of the charge of an electron, it would look like this. It would be 1.602 times 10 to the negative 19. All right. So now if you think about what you've really done, you've represented numbers, this number right here, where you have one bit or one digit to the left of the decimal point and then some numbers to the right. And then you have this multiplication factor, which essentially moves or tells you how far you moved the decimal point in order to represent it in scientific notation. So in this way, you can think of it as floating the decimal point, okay? All right, so now when you move into binary, it's the same number, right? Except that you multiply it by the base raised to an exponent. So the technical or the official way that you represent a real number in binary is you have the lower part right here, which is actually called the mantissa, and then you say times 2 raised to the exponent. So if I go back to this decimal example, notice that I said times 10 raised to the exponent. That's because the base of these numbers was base 10. This is officially the mantissa, and this is the exponent, and this is the base I raise it to. So in binary, that's the same form. Now, you have two very common floating point formats. One is using 32 bits and one is using 64 bits. So if you look at how you break down a 32 bit into floating point, you basically have 23 bits that you reserve as the mantissa, and then you have 8 bits which represent the exponent, and then you have a sign bit. Okay, so this is very important. We do not use 2's complement to represent in negative numbers in floating point. We use the most significant bit as a sign bit, where 0 is positive, 1 is negative. And then if you look at the mantissa, you got 23 bits. So it can be a very large number of bits, but you can move the exponent like crazy. Like you can move it way to the left, way to the right, and you can represent very big and very small numbers. And by big, what it means is that when you go back to this decimal example, if you have a positive number up here, that makes the number bigger. And if you have a negative number in the exponent, that makes it smaller. So that's what we mean when we talk about big numbers and small numbers, okay? This is called single precision. Okay, so 32-bit floating point numbers are single precision, and we'll talk about what that means in a second. And a 64-bit floating point number is called double precision. And what it means is that you just have more bits for the mantissa and more bits for the exponent, and that means you can represent, more precise numbers, but you also can have a huge, huge range of big and small numbers. Okay, so data types in C. If you want to encode a number using 32-bit floating point format, it's called a float. That is 32 bits, it's 4 bytes, and let's look at the range that you can have. plus or minus 3.4 times 10, exponent, and this is in decimal, plus and minus 38. So it's huge. The range is absolutely mammoth, okay? However, when you convert the bits of the mantissa back to significant digits, so the bits in the mantissa are in binary, and you look at how many digits in decimal that you can actually represent, you only get 6 significant digits. Okay, and that becomes the issue with a single precision floating point number, is that the significant digits, or that what we call the precision, isn't terribly good. Okay. So then what happens is that you say, well, I want to move to something more precise. So you move to the next data type, which is called double. So this is double precision, but double is the word you use. And it is 64 bits of memory usage. And look at the range, 1.7 e to the plus and minus 308. So you're so big, it's just, you never would have used all that. Okay. It's just huge. But you do get 15 significant digits. Okay. And then you go to the next one, which is long double, which is 16 bits. And I think it has more significant digits. I mean, I've updated that. You hardly ever use long double, but it's got this exponent that's so crazy. You'd never use it. And then you get more precision, significant digits. Okay. So floating point numbers are representations. There's no guarantee that every real number can be represented exactly. Some can, like you can represent 0.5 in floating point, and it is perfect. 0.25, perfect. 0.125, perfect. But not so much like 0.126671. You just get close. So there is error involved, and that's where you see it in the significant digits, okay? All right, now the range is huge of floating point numbers, but precision is not. So precision is what kills you. When you get to a microcontroller, usually a 32-bit, processor, floats can be used. So you can use float, and then you do see errors in the precision as you do operations on them. So you can actually see the precision become noticeable. Precision means that as the operation goes, the result is less and less accurate. So the answer should be like 2, and the result the computer gives is like 2.1, 2.2, 2.3, 2.4, and it goes further apart. So floats are good for microcontrollers, single precision. Doubles are usually what you use on a workstation. So when we talk about our CSCI 109 server, this is this big Linux server. It's got tons of memory. We usually use doubles for everything because the doubles don't have as much of a precision issue. Long doubles are only used for like specialized computing applications. I've never used a long double, to be honest with you. But anyway, let's code along and let's see how this works. Okay, so I've got a couple terminals over here. I've logged into the CSCI server. If I take a look at where I'm at, I'm in my home directory. Let's take a look at what's in here. I'm going to go into my mod 03 code along. So I'm going to change into mod 03 code along and take a look what's in here. And I've got some prior code in there because I was messing around in earlier videos. And here I'm in home directory, and let me change into mod 03, and that's where I'll compile. And so now let's go ahead and make a new file called printing_floats.c. So I'm going to go vim printing_floats.c. Okay. All right. So I'm in Vim, and I'm going to go into insert mode by hitting I. And let's get a comment header here. So I'll do like playing with floats. All right. So there we got that. And now let's do our C program shell. Okay. So what I'm going to do is I always do pound include, and I go stdio.h, and that brings in the standard IO header file, which has the printf function in it, which I use for everything. Now I want to do the main function shell. So I'm going to go int main void open curly, come down here, return 0, and then close curly. Now I've got my shell. Okay, I can even save it at this point. I hit escape to go into normal mode. I go colon to put in command mode. I hit W to do write, and I'm done. Okay, so let's take a look at this. Let's set up some variables. So let's set one up that's a float. So I'm going to say float. Notice it turned green. That means it recognized it. And then let's call it like var3, and we'll go 3.14. Okay, all right, that's good. Let's do another one that's a double, and let's do var4, and let's do something like 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Boom. And then let's do one more float that is like a charge of an electron. So QE, and then we'll go 1.6. And guess what? You can represent scientific notation in C by simply using the E as in the number. So this is perfectly valid to represent scientific notation. So let me save that, make sure we got no issues there. And life is good. Okay. You can use upper or lowercase on this. So whatever is good for you. But there you have it. And you know what? Let's be accurate. Let's make this negative. So okay, there we go. Now, of course, you gotta line your variables up, make it look nice, and line up the equal sign, make it look all pretty. All right, life is good. Now, let's take a look. That's how I did it. Now, when you do floats, I mean, they're very similar. It's very similar to ints. It's just the data types and they have keywords. Let's now look at using printf and let's look at some of the options you can have here. So printf, again, can print floating point and you have format specifiers. So %f will be floating point, okay? So this is good for floats. So I'm gonna watch this. I'm gonna do printf, and just like last time, I'm gonna go var3 holds, and then I do a format specifier, which is gonna be %f, and that's going to tell C, hey, I want to print the value of a variable that has the type float, and I want to put it right in this location. And then it goes to new line. I end it, and I'll go var3. Okay. All right. So let's compile that and make sure that everything's cool. Let me move that just a little bit. I'll move this over here, and that's it there. So now I'm sitting here, and I'm gonna do around this little fellow over here. I'm gonna go GCC, and I'm doing where am I at here? I'm gonna do GCC print underscore floats, and then I'll go -O, and I'm gonna do print floats, and I'm gonna go like that. Okay. Now I'm gonna do wall and see what kind of warnings I get. If I define a variable and I don't use it, wall will tell me that I'm doing that. It'll say warning, unused variable. Okay, so that's what wall really gives you. Let me compile this without wall and then we'll run it. So I'm gonna do ls. Here's my print floats executable, no extension, and it's green. So I'm gonna do Sunny Holland, right? Look in this location, print underscore floats, and I run it. var3 holds 3.140000. All right, life is good. Life is good. Okay, let's go ahead and do this. Let me do another printf, and we'll do var4 holds, and then let's do float on this one. Now, you're probably going, wait a minute, do you use float for both? And it's like, you know what? You can, but you also have something else you can use that I'll share in a second. So I'm going to go ahead and go GCC, and then I'll run it. And it's like, it didn't work. Why did it not work? I didn't save this, I don't think. So let me save that, and then let's go over here and go GCC, and then run it. Okay, so 1, 2, 3. Oh, I got some weirdness going here. Let me make this so it matches the example in my slides, just so we can do it. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I'm gonna come down here. Let's save that up. Save it. Compile it. Let me clear that before I run it so you can get a clear screen. Go. All right, so we got 1, 2, 3, 4, 5, 6, 7. Dot 1, 2, 3, 4, 5, 7. What happened? Well, it actually rounded for me. Okay, so it actually rounded because you're running out of room. Let's go ahead and print QE. So this one will be interesting. So let's go printf, and then let's do this QE holds, and then I'll do the same thing with float. And it's like, man, I don't know, is float gonna work for this? And then we'll go QE. I save that. I come down here, pile it up, pilot, run it. Let's go clear, run it so you can see. Okay, QE didn't even show up. And you're like, why didn't it show up? And it's like, well, by default, this is only gonna show me like 1, 2, 3, 4, 5, 6 after the decimal. Okay, because that's kind of the precision that you have. It's like the fractional components of this. And so it gave me 6 zeros, which is like, well, yeah, but the number's like way over here. So immediately you get in a point where you're like, you know, I need a different format specifier or different ways to do this. So let's take a look at using options such as width and precision. So if you come in here, you can use a dot between the % and the actual format specifier letter in order to give it information. See, and you can specify the precision and the width. So as an example, watch what happens if I go to I want to like limit the number of digits after the decimal point to the right on this pi to only be 3.14. So I could come in here and I could do this. I could say insert dot two. So that would limit it. So now if I compile that again and I run it, it's like, oh, 3.14. That's kind of cool. That's kind of cool. And then let's not let it automatically round the next one, var2, or excuse me, var4 to 6 digits. Let's make it print the whole 7. So I'm gonna come down here and I'll go, okay, dot 7. Okay, and it's like, okay, that's cool. I'll GCC and run it. Okay, that's cool, that's cool. And then for this one, you got to do like dot 22, which is 22. So then let me compile that and run it. It's like, oh man, that's awesome. So let me clear that and come back up here. And it's like, oh, that's cool, 1.6. Now I didn't give it a lot of accuracy, so let me do this. 1.602, which is a little more accurate. And let's do GCC, clear it, good. Okay, so now you're sitting here and you're like, well, that's kind of cool. What does the width thing do? And it's like, well, what does width do? Width will pad on the left of the whole number spaces. And it's really used to just for formatting if you want to like align something. So as an example, if I want to notice that var3 and var4 hold values, but the decimal point is kind of not lined up and I wanted to make it look pretty, I could basically pad this and go, I want 1, 2, 3, 4, 5, 6 pads on here. And I could be, yeah, so let's try this. So I'm gonna come in here. Let me put let's put 6 and see what happens. So that should move this 3.14 over a little bit. So I do that, and look at it, I moved it 1, 2, 3, 4. Now it's moving like the whole thing, including some of the characters you don't see. So you got to kind of play around with it. So if I do 7 and then move it, precision is evaluated first. So notice how it's moving over. So then I'm like, okay, so if I move this like 10, it might get lined up. But what's going to happen is that as soon as I move the precision around again, it's going to move that. So let me clear and show you. So there it is. Now they're lined up. So I basically had to move this thing over. Yeah, and so whatever. So that's how you pad the front and then you determine how many digits are in the back. All right, now let's look at this. Another thing that's really important is there's another format specifier which is called LF for long float. So let me come in here and I'll show you this before we look at like the garbage stuff. So I'm going to come in here and I'm going to do long float on here, LF, and that's what you use for doubles. So it's long float. And you're like, why didn't you use LD? And it's like, well, LD was taken by long decimal. Okay, so let's look at the default for long float format specifier. And then let's see what happens here. So compile it, run it. Now, yeah, it worked all right. So whatever. So var4 was a double and it's still printed the same way. So long float, life is good. Okay. But anyway, float is %F is for floats, %LF is long float. And then you come in here and you can alter the precision. All right, so let's do this. I want to show you this little example right here. So I'm going to come in here and I'm going to do 30 and 22. And then let's come down here and do .22. And then we'll do 30. Okay. And then let's compile it and run it and see what I get. Okay. All right. Life is good. And okay, life is good, life is good. Now, I didn't save that, did I? Hang on here, let me save this. Save, and then compile, and run. Okay, let me clear this and run it. Not saving is a very common thing that'll frustrate you when you're trying to figure out what's going on. So let me clear the, slow down. Let's just slow down this. Print. Okay, so I'm sitting here and I've got 3.14, which was the number I had, and then I've got 0000, and then I got all this garbage that came in here, and you're like, what's the garbage? And then same thing here, I've got like 1, 2, 3, 4, 5, 6, and then I've got 1, 2, 3, 4, 5, 6, 7, and then I've got my zeros, and I've got all this garbage, right? So what I did was I put the precision in here, so I had 22 digits of precision, and in order to get it to line up the way that the width is like how big the entire number is. Okay, so including the fractional parts. I don't use width hardly ever, right? Hardly ever use width, but I use precision constantly. And so when you think about like 22 digits, I got 22 digits over here, and then I've got 8 in front. So that's why you had to put 30. It's because the whole thing, it's like how big do you want your entire word, right? And so in this situation, I did this and I kind of lined up the decimal points. However, check this out though. When you look at this, you've got all this garbage in the end, and you're like, what is the garbage? That wasn't there to begin with. Well, that is just the accuracy. So you really only get, this is a float. So 1, 2, 3, 4, 5, 6, 7. It's like 6 or 7 digits of accuracy. And then it just, who knows what you get. Okay. It's just garbage. Same thing over here. This is a long, this is a double or a long float, and it's going to be like 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. You get about 15 to 16 places of accuracy, and then it's just garbage. Okay. All right. So that's an example of just, that's what happens. Okay. That's what happens. Now, when you look at this, if you, in this example, you see the garbage over here and you kind of are like, okay, I get it. 1, 2, 3, 4, 5, 6, 7. Well, when you talk about significant digits, you include the whole and the fractional. So when you go to the double that has like 15 digits of accuracy, it's the whole number plus the decimal and then whatever's left, then you get the garbage. Okay, so then you get the garbage. Okay, so life is good. Now, this is cool. Now the question becomes, how come 1602 didn't change? It's because the zeros are not considered significant digits. This actually only has 4 digits of precision. It only has 4 significant digits. Okay. All right. Life is good. Life is good. Okay. So we're rambling on here. Here's some more format specifiers. So when you use doubles, you usually use long float so that you get the full functionality. So let me get in here and do long float on the double. And you can also use scientific notation. So if I come in here and I did E and I looked at how that would print the Q. So I'm going to come in here and I'm going to compile this and then run it. Look at this. Oh, baby. I've got negative 1.602 e to the negative 19th. It will automatically put it into scientific notation. And then if you're like, well, I'm an uppercase E person, it's like, well, that's fine too. Go ahead and do that and then run it and it'll put the uppercase E in there. And then you're like this, hey, I don't want all, let me run that. I don't want all these zeros. Well, you know what? You can still use the dot, precision option, and you can come in here and do this. So I'm going to go over here and I'm going to compile it and run it. And it's like, oh baby, I can format it any way that I want using these precision. Okay, so here's the kind of the summary of this. Floating point numbers are real numbers. You have 2 types you're going to use, float and double. Float is called single precision, 32 bits. Double is called 64 bits, called double precision. You have different format specifiers for printf to use. So you use %f and for single floats, and you use %lf for double. Even though they both work, like float will work for both, you just usually use the same one, or else you'll sometimes run into errors. But you can also do scientific notation. All right. And then you use the format options, so precision and width, in order to kind of make them look like what you want. For long double, the format specifier is capital LF. All right. But again, I've never used a long double, so you never will too. And that is it. That is how you do floating point numbers in C and how you print them in printf with format specifiers. All right. See ya.